So welcome to our Potpourri meeting. Again, my name is Randy Atwood, and I will chair the meeting tonight. We're getting close to the solar eclipse. Yeah, so we're going to probably some of our meetings are going to be focusing on the upcoming event as it is quickly becoming, well, it was for a few days there when all the school boards bailed. So now it'll be quiet for another 6 or 8 weeks before the big event. So we've got some presentations from members tonight. Our first presentation is by Dr. Chris Malicki, who has seen over 400 solar eclipses. Oh, 16 total? Oh, you said 400 earlier. Oh, okay. Only 16 total. Okay. So if you heard that they are once in a lifetime events, no, they're not. How many have I seen with you? 3? So Chris is going to talk about an interesting aspect about a solar eclipse, maybe not something that you'll see at your first total solar eclipse, but something that you should look for at some point, the flash spectrum. So Chris, it's all yours.
All right, so you're going to see the eclipse of the sun. As most of you know, the 1 minute just before totality, it becomes really exciting. There's so much to do and there's so little time. There's shadow bands to look for. They appear 1 minute before totality, so you're looking down at them. But at the same time, Venus is there, which you probably saw a minute ago, and now you can see Jupiter naked eye, even though it's not total eclipse yet. The environment is rapidly getting dark. The temperature, you've noticed it's getting cool. The wind that was there before has stopped. You're noticing that, but if you're noticing that, you're not noticing the other things, and things are happening very quickly. Birds are confused. Dogs and cows don't know what to do if you have them near you. If you're near a rooster like I was in Chile several years ago, right after the eclipse, the rooster was just going crazy, making it crowing, whatever roosters do. Right after totality in Bolivia, flamingos flew thinking that it was nighttime. So mind you, this is right after the total eclipse, not before, but still there is animal behavior before as well. You're also, while you're doing all that, looking at the shadow bands and noticing all the other things, a huge wall, black wall, is rushing towards you. That's the shadow. If it's a little bit hazy, like in Gimli, Manitoba in 1979, that's extremely dramatic and frightening. It's like a big wall coming at you. So you're looking at that. It's changing all the time. But if you're looking at it and watching its evolution, you're not seeing these other things. And right before totality, that shadow becomes a cone and blends into the sun, and you could see it merge into the sun. In 16 eclipses, I've never seen that happen, and I would really love to do it this time, except there's just so many other things to look at. The corona has appeared. It's 30 seconds before totality. You can look naked eye glance, of course, no magnification, but you're glancing, you can already see the corona around the sun and the diamond ring, and through it, meanwhile, you're rushing to your telescope and looking at Bailey's bead, filtered, of course. All this you're doing in 1 minute. At the same time, you've got your camera there. You have to make sure your lens was on for the partial phases. You have to take off that filter because you want an unfiltered view of totality. You have to make sure you know that the camera is pointed where the sun will be 4 minutes later. If you have a video recording, you have to make sure you've put it on. You have to do all of this in 1 minute. Imagine that. Yeah, that's the slide I want. And now, in the 1 minute before totality to the 15 seconds after, I'm asking you to do one more thing. You're to look at and or photograph the flash spectrum. Okay, so the Observer's Handbook is very well organized. Pages 136 to 147, 126 to 147 are dedicated to eclipses of the sun. So that's the same year after year. Those pages are eclipse pages if you look in the Observer's Handbook. In the year 2022, there was no total eclipse of the sun, and there was extra space. There's 5 extra pages. So on 3 of those pages, Jay Anderson had an article, How to Watch a Solar Eclipse, and that article hasn't appeared in subsequent observers' handbooks because they've all been filled with eclipse information for that year's eclipse. And this really intrigued me. Jay wrote, the flash spectrum visible for a few seconds at second and third contact during a total eclipse before and after totality when the photosphere is covered is the solar atmosphere's innermost layer. Within the last minute before totality, the diffraction grating will show at first a continuous rainbow band of colors from the photosphere. As more of the photosphere is covered, the continuous spectrum narrows and disappears. That's the continuous spectrum, that big band coming from that Bailey's bead. And the colored horns, which you see on either side, grow towards the middle, eventually joining to form a crescent. The first few colored arcs will be joined by many others as the instant of second contact approaches. The rainbow of colors is from the photosphere. That's this big band in the middle, blended into a band continuous color from indigo to red. The distinct color horns above and below the continuous spectrum come from the chromosphere, each one associated with a distinct element. So when I read that, it really intrigued me. So I did a bit more research. So what Jay is talking about, this is on the left is about 1 minute before totality. You can see that really narrow crescent, and there's chromosphere above and below it. And 1 minute later, you've got the view on the right where you just see the chromosphere. So that's what we're wanting to look at. The crescent and the chromosphere is very narrow. It's very well resolved in the horizontal direction, but it's very wide in the vertical direction. So you've got really good resolution sideways, but not vertically. And this will become very relevant as the talk goes on. The sun spectrum is, it's really long, but chop it up into pieces and make it mount it one on top of the other so you can see the whole thing is a long rainbow band with numerous black bands across it, the absorption lines. These are from different elements. So that's the normal spectrum of the sun. In 1968, a French astronomer, Jules Janssen, used a spectroscope on solar prominences in India during the total eclipse of August 18th, 1868, and observed bright lines. Subsequently, he was able to observe prominences outside of an eclipse. When he studied the position of the yellow line, he realized that it did not correspond to the yellow doublet of sodium, but was from a new element which was eventually named helium after Helios for the Greek sun god. So the second most common element in the universe was discovered in a solar prominence. So in this image, you can see the yellow line is helium and the red and violet lines are hydrogen. Now, Len Fulham, I emailed him and I got permission from him to use his images. He was very kind. He sent me a video and he said that I could use whatever I would like from his images. And I think it's important to get permission, especially for copyrighted images. Now, to me, this is a very exciting description of an eclipse. So you're going to an eclipse, there's clouds, and you don't know if you're going to see it or not. And for 5 minutes, a hole in the clouds appears and you can see the total eclipse. It's just so thrilling. So Charles A. Young was in Spain for the total eclipse of December 22nd, 1870. And here's the report from Scientific American issue, March 5th, 1871. Early in the morning, it clouded up and even rained from time to time. The party made their preparations, however, and before first contact at 10:25 a.m., there were many patches of partly clear sky. At the moment of total obscuration, a small rift in the cloud passed over the sun and permitted the observer to see sublime phenomenon in a satisfactory manner. Within 5 minutes after the end of totality, the sky was wholly clouded. The astronomers did not see the sun again till just that evening after a heavy storm of wind and rain. By means of the spectroscope, 2 or 3 lines, iron lines were observed, also 2 barium lines and a magnesium line, and at the base of the chromosphere, a thin layer in whose spectrum the dark lines of the ordinary solar spectrum are all reversed. So it's called the reversing layer. During the total eclipse of December 22nd, 1870, American astronomer Charles Young observed that the dark absorption lines in the sun's spectrum, so look at the image, see that big band, that's a continuous spectrum. It has, if you magnify it, there's absorption bands. So for a brief time, that disappeared and you saw bright lines instead. So instead of these dark bands in a continuous spectrum, you saw bright lines. The lines that were previously absorbing the bright sunlight now showed in color without being drowned out by the brilliant photosphere. Seconds later, as the moon covered the reversing layer, these lines disappeared. He had just discovered the flash spectrum. We now call the reversing layer the chromosphere, the chromos being Greek for color. So that's what we would like to be able to observe. So Len Fulham gave me permission to use this image from Astronomy Picture of the Day. So in a flash, the visible spectrum of the sun changed from absorption to emission on March 9th during the total solar eclipse. After that fleeting moment at the beginning of the total eclipse phase is captured by telephoto lens and diffraction grating in this image from clearing skies over Ternate, Indonesia. At left, the overwhelming light of the sun is just blocked by the lunar disk. The normally dominant absorption spectrum of the solar photosphere is hidden. What remains, spread by the diffraction grating into the spectrum of colors to the right of the eclipsed sun, are individual eclipse images. The images appear at each wavelength of light emitted by atoms along the thin visible arc of the chromosphere and in an enormous prominence extending beyond the sun's upper limb. The brightest images, the strongest chromospheric lines are due to hydrogen atoms, produce the red hydrogen alpha emission at the far right and blue hydrogen beta emission on the left. In between, the bright yellow emission images caused by atoms of helium, first discovered in the flash spectrum. I'd be ready to show the video now. These are from that video,
Oh, cool.
stills from that video. But I'd like to show the video per se. Okay, so let it run. This is the 1 minute video that Len kindly gave me permission to show. Yeah, it's running. So he's very close to the center line. No, it's very close to the edge. So you've got Bailey's beads, and you can see they're causing a continuous spectrum, but there's chromosphere on either side of that bead producing those colored images, the flash spectrum, just like Jay Anderson had described. And now it's, so he did a video. Like, you guys could do this video. Just put a diffraction grating in front of the camera and do a video, and that you can get that. Isn't that cool? Okay, so yeah. Okay, I think we're
That's
good.
cool. Okay.
Yeah.
And then we'll tap back.
You
When it's not here, I'll help this.
can't see anything.
Are you ready?
Yeah, we can go on. Thank you for your help, Alan. Really
Yeah,
appreciate it. So we want to get back to the presentation.
No, that's not right.
So that showed you in real. Okay, so I took stills from his video. He was 500 meters inside the southern edge. So at the very top, you see a very large, like a beading or a crescent. So it's causing this large continuous spectrum that the sun normally has, but you already see time on the look at actually on the second image, there's chromosphere around that beading. So the continuous spectrum is narrower, and you see the flash spectrum starting to appear, these various spectral lines, and it shows up really well in the third and fourth image. And okay, there's that one. Okay, so thanks to Len Fulham for sharing these with me. Okay, and there's just individual images. Okay. Eugene Quinn, astronomy picture of the day, September 7th, 2017. This is from the great eclipse in the US in August of 2017. I emailed him. He gave me permission to use his images. So that's his images of the flash spectrum. He's superimposed a couple of images, as you can see. So explanation: in Madras, Oregon skies, this colorful eclipse composite captured the elusive chromosphere or flash spectrum of the sun. Only 3 exposures made on August 21st with telephoto lenses and diffraction grating are aligned in the frame. Directly imaged on the far left, the sun's diamond ring-like appearance at the beginning and end of totality brackets a silhouette of the lunar disk at maximum eclipse. Spread by the diffraction grating into the spectrum of colors towards the right, the sun's photospheric spectrum traces the 2 continuous streaks. They correspond to the diamond ring glimpses of the sun's normally overwhelming disk, but individual eclipse images also appear at each wavelength of light emitted by atoms along the thin fleeting arcs of solar chromosphere. The brightest image or strongest chromospheric emissions are due to hydrogen atoms. Red hydrogen alpha emission is at the far right with blue and purple hydrogen series emissions to the left. In between, the brightest yellow emission is caused by atoms of helium, first discovered in the flash spectrum. Okay, so how are we going to observe the spectrum? Well, to produce a spectrum, you can use a prism like at the top, or you could use a diffraction grating. A diffraction grating has lines and light goes through it, and as the light goes through, because of quantum mechanics, light is a wave and a particle. It spreads out into a spectrum, and you get areas of constructive interference, constructive interference and destructive where it disappears. So you see all kinds of rainbow colors. I'm in no way going to try to explain the optics of this. I'm not an expert, but essentially that's how a diffraction grating works. So how do you get a diffraction grating? Well, you pay $8.91 to Etsy, and you get one from Ireland. There's a diffraction grating in here. It's part of the raffle we're going to have. So that's from Etsy.
We're just supposed to trust you?
Well, you can, well, if you win it, take it out and look at the lights. So it has, they say 20,400 lines per inch. So I calculate, that means they're 1 micron apart. That's about right. I have 3, I bought 3 diffraction gratings. So I fooled her. There's almost nothing on the internet about using a diffraction grating during an eclipse. Like I searched, like, is it safe? Like, can you look at it? Like what direction has to be? Nothing. I had to do all these experiments myself. So I took the diffraction grating out, and there you could see it in the kitchen being shone at lights outside, and you're getting all these beautiful rainbow colors. I decided to look at this a little bit more intensive. So I took my son's microscope. I used the maximum power 200 times. And even at that power, I was unable to see lines in the grating. Like, I wanted to know what direction they are. Like you want them to be parallel to the solar crescent, not horizontal, no, not perpendicular to it. So I couldn't figure out by looking under a microscope what direction the lines are. So I took a Christmas light bulb and I held the diffraction grating one way, and then I rotated it 90 degrees in another way. And that's the 2 different images I got. So when it's held horizontally, you see the image on the right. And so you need to know what direction it is because you want the lines to be parallel to the crescent. So you can see light that goes through the, just rotate those 5 black lines like 90, like keep them pointing up, but just rotate them so the light is going in between them. And that's the direction that you want the diffraction grating to be in to show you a spectrum like this. Okay. So I found no information whatsoever anywhere about how safe it is to look naked eye at the solar spectrum through a diffraction grating. Like I took the diffraction grating, the sun was shining, I held it like that, and you could see the nice spectrum way off to the side, and it looked quite safe to use. And I think the sunlight was rarefied into a big spectrum. Nonetheless, I think it behooves us to have a warning if you're going to look at the flash spectrum with a grating. You do not use any magnification while you've got the photosphere, like while there's still a diamond ring. Certainly during eclipses, and there's no children here to run into a dangerous thing. So at eclipses, I usually try to see the corona, the first appear. So it's not total eclipse, and I'm glancing at the sun like this, and oh, there's a corona, and I'm not staring, but half a second, I'm seeing it. So I think to look when it's not yet total eclipse and you're looking at the flash spectrum, you're not looking directly at the bright diamond ring. You're looking to the side where the spectral lines are, and you wouldn't stare at them. You would glance a little bit, but once the total eclipse begins for the 15 seconds of the chromosphere, you could stare safely all you want. And of course, for photography, you just put a diffraction grating in front of your camera lens, make sure the direction is correct, parallel, and get some great shots. Thank you, everybody. Yes, it is. It's a real-time video. It's a telephoto lens with a diffraction grating in front of it and just looking at the sun in video. You could take that, make a lens out of it, and do a video like that.
Chris, any idea how you would measure the wavelengths of the images?
You'd probably have to compare it to, you'd have to probably compare it to a published spectrum of elements. The colors I'd mentioned in my presentation, yellow, I'd like to be able to see a helium line, so that's what I'm going to try to do during the eclipse.
Okay, great. Thanks a lot.
Okay, thank you.
I gave the same talk 2 nights ago to the Toronto Centre, and interesting, it's exactly 2 months to the day between the two talks. And I started out by saying eclipses are so fascinating, and they're even more fascinating than I thought after the last talk. That was really neat. Anyway, the question of predicting eclipses is something I've always wondered, and you hear stories, so I decided to look into it. And very quickly, I found out about the total solar eclipse of Thales. And the prediction from the experts who can look back in time to what eclipses would have been in the area of Greece and Turkey when it could have been. And they figure it was probably 585 BC or minus 584, because there's no zero in the BC AD system. So it's slightly different. Herodotus was born 100 years after this event. And so obviously he couldn't talk to anybody that had personally seen it or anything, but he get it as a little bit like me writing a story about some meeting leading to Canadian Confederation, which was 100 years earlier than when I was born. Well, actually less than 100 years. Anyway, this eclipse started, wait a minute, is there a mouse? Can you see the mouse cursor?
Yeah.
Okay, so it started on the Western Pacific near Central America. The central greatest eclipse point was somewhere in the middle of the Atlantic, probably around Bermuda, and it went across Greece and Turkey. And I have quoted all the words, but it's really wordy, this description. So I've only put part. Basically, 2 cities were at war with each other for 6 years. And then just as the battle was growing warm, this is the direct translation from about 100 years ago, day was on a sudden changed into night. What could that be other than a total eclipse of the sun? I remember one intense thunderstorm when the clouds were green and it was too dark to read. And I huddled my family into a safe place down in the basement just in case there was a tornado. And a few minutes later, we could hear sirens of ambulances going to places that were actually affected, but we were okay. Anyway, when it was over, because people back then were really superstitious about events and gods and messages from God and everything, the kings decided to make peace. Then the next line is, this line had been foretold by Thales, who lived in third city, and he told people in a fourth city about it. Wow. What? 2,500 years ago, somebody predicted eclipses? And then the account goes on to say, fixing for it the very year. Is that a prediction of a total solar eclipse? And it reminds me of a wise philosopher who, when a punk approached him with a switchblade, he said, "That's not a knife." Just, there's no way that to me is a total eclipse prediction. I personally think, and there's no official word on this, this is just my thinking, if you're saying you're making a total solar eclipse prediction, I think it should have a specific date and a specific location of totality. Basically, it lets you chase eclipses. And an example of that is the one we're going to enjoy in 2 months less a day. And where's the mouse? And it starts in the mid-Pacific, below the equator. And it goes up with the greatest eclipse being in Mexico. And then it goes tantalizingly close to Mississauga and Toronto, but not quite, but it's close. And then people in the west coast of Ireland will be able to see the partial eclipse as the sun sets. A total solar eclipse can only be seen by something like 1/3% of the Earth. A little less than 1 in 400 years is the average time that a given site on Earth is going to experience a total eclipse, and then the next one. In other words, other than people lucky such as those in southern Illinois, you are very unlikely to see two total solar eclipses unless you chase them. But the lunar eclipse covers over half the Earth, can see totality. And basically, my message is ancients could find patterns that allowed them to do a half-decent job predicting the lunar eclipse, and not a bad job predicting a partial solar eclipse. But I've seen no evidence that they were able to actually say this city is going to get an eclipse on this day. So I guess I'm giving the game away. Want to now bounce to early religions. There are groups of people called priests, shamans, astrologers, whatever, who made sense of the existence of peasants, etc. And they often invoked supernatural beings, and often those supernatural beings were astronomical objects like the crescent moon here, or planets, or whatever. Now, the impact of an eclipse emotionally, I'm going to display with a story. A scientist flew down to Yucatan, Mexico to do weeks of field work. And she billeted with a Spanish science teacher whose ancestors were Mayan. And the two ladies had a wonderful time after hard days of work, talking and whatever, and philosophically, they really enjoyed each other. And then a total lunar eclipse came over that area. And it was interesting that this educated science teacher, who probably copied the same eclipse diagrams that we did when we were in school, at least, actually, how many copied the eclipse diagrams? I'm just curious. Did you copy one in school? No? Yeah, a few people. Anyway, my point is that the lady that had Mayan ancestry was in absolute terror, and the emotional pressure on her with this eclipse, even though she had studied all the theory. And that's, I think, a key to astronomy. More on that later. Now going to science, and the orbit of the Earth is flat around the sun. And the orbit of the moon is tilted about 5 degrees compared to the orbit of the sun. And where's my cursor? So for part of the orbit, it's below the plane of the Earth's orbit, or the ecliptic, and part above. and it crosses at either descending node or ascending node for us who live in the Northern Hemisphere. And maybe Crocodile Dundee would disagree with that, but too bad. Oh, I meant to mention something. Oh, yes, here. I put a white dot that actually is much bigger than the actual moon, showing that on April 8th, it's going to be close to the node, and when it's new, and we're blessed to have a shadow that comes everywhere but Mississauga and Toronto. This eclipse will be in front of the stars of Pisces. And if there were a lunar eclipse on the same day, which ain't happening, the eclipse would be in Virgo. So in 3 months' time, the moon's orbit is tilted roughly the same way. And now it's well above the plane of the Earth's orbit, so there are no eclipses. But a few more lunations later, you have eclipse season. And I wrote in a way that I can't change. I said at least one lunar and one solar eclipse somewhere, but the odd eclipse season doesn't have a lunar eclipse. I hadn't realized that, but that's something I saw. I think there are 2 of them in the 21st century that are like that. And you have 12 lunar cycles. You don't quite make a year. And some calendars are based on lunar. And the just today, a lady in a store wished me Happy New Year because today is the Chinese New Year. And I asked her, is that follow the moon or is it always roughly at this time of year? And she confirmed that it's, when they need to, they add an extra moon to make it whatever. I don't know the details of that. What is it? Swiss cheese. Anyway, now, if the moon were only affected by the Earth's gravity, then the direction of the line of nodes would be the same always, and every eclipse would be in either Pisces or Virgo. But the sun affects the moon, even though both the moon and the Earth are going around the sun. The sun affects it in a way, and I don't understand why, but it tilts the line of nodes a little bit. So 19 degrees, and I made this angle to be 19 degrees, even though the view is from an angle. It tilts at 19 degrees every year. And you have eclipse seasons every 5.8 years. And you also have a similar pattern with the perigee and apogee, but I haven't got diagrams for that. These combine into all sorts of interesting patterns. And the most common pattern was discovered by Babylonians thousands of years ago. And I'm going to explain how they did it. I think a big driver is there was some belief that the kings in Babylon must not be exposed to light from a lunar eclipse. For some reason, it was felt if that happens, they're going to die, and kings have a habit of not wanting to die. And I wonder if that's one of the reasons they had a whole cadre of, whether you call them shamans or priests or astrologers, whatever, people that followed astronomy, and that was their job to do that and to predict eclipses. They kept detailed records in Babylon, and I have differing dates, but it's something like 500 to 1,000 years of data. And they kept this on clay tablets, some of which still exist and some have got damaged, so they don't have a continuous record. Of course, they write special events like eclipses, comets, a new king coming to power, et cetera, et cetera. But they also recorded a whole bunch of details of the moon events. And looking at those details, not the eclipses only, but those details of how the moon is relative to the sun and timing and all that sort of stuff, they were able to detect patterns. And it was somewhere around 800 BC that somebody figured it out. I've emailed a number of people to find out if they also measured the azimuth or bearing of the moonset and sunset, because you'd think it would be fairly easy to have an observing place that has a flat horizon and to have something that records the angles, because back then they had angles. But I haven't been able to find, but that would make sense that that's part of the patterns. And when you combine all those patterns together, you get the Saros cycle that was named by Edmund Halley rather than then. And they found you get repeats every 18 years, 11 days, and 8 hours. The modern explanation is each of the cycles, nu, node, and perigee, they have a certain number of days each happens, 29 days, a little bit more, a little bit less. And it turns out a certain number, 223 nu cycles gives a number of days. A larger number of node cycles gives almost exactly the time. And the perigee cycles are almost all the same. And this is what ancients discovered by all that observing, recording data, and analyzing it. And the number 223 is printed on the Antikythera, what's it called? Mechanism? I can't read it. Anyway, that number is printed. So obviously the people that made this, and I think it's like 100 BC that it is. So anyway, I'm now going to illustrate total eclipses in the same Saros cycle. Did anybody go to the 2006 eclipse? 1, 2, 3. And it started off Brazil on the other side of the Atlantic, a little south of the equator. It went up. The greatest eclipses in Libya. Then I know some people who saw it in Libya in the desert. Did you guys see it there? Okay. And I have another friend who saw it in South Turkey near Antalya. And apparently the weather was lousy, but the eclipse moment was just right. So that's all people care about. And then the eclipse kept going through the various stand countries, and I don't know anybody that went there. What happens 18 years, 11 days, and 8 hours after that? 2 months and a day, less a day. These are both in the same Saros cycle. Notice that both start about the same distance below the equator. Both of them go up. They're the ascending node. The greatest eclipse is roughly the same latitude, and it's roughly the same shape and roughly the same width. And that's a Saros cycle. And but it's not the same spot in the Earth. But there's 8 hours. And what happens is the Earth is rotating, so it goes east over 1,000 kilometers an hour. And in those 8 hours, instead of the eclipse being over Africa, it's over Mexico. Now, let's think about 2024. Anybody want to guess where the eclipse might be then? 8 more hours, a third of the way around the Earth. It's in the Pacific off China. Sorry, 2042. Sorry, did I say 2024? Sorry about that. Anyway, 2042. There's going to be an eclipse off China and in the ocean, and it goes over the Philippines. I don't know whether it's something that people are going to follow. I don't think I'll be alive in another 18 years, but I might be, but who knows? Oh, is that part of the same Saros cycle? Okay. Okay. Anyway, but if you go another Saros cycle, it goes another 8 hours around, and you get another eclipse that the greatest eclipse point is still in Libya, in a different spot. So when you have 3 Saros cycles put together, they combine together to make eclipses that appear in roughly the same spot of the Earth, and that's called exoligmos. Now, I have done some really stupid things in my life. One of the stupidest is some friends came to me at university and said, Ron, we're driving to Virginia to see a total eclipse of the sun. Do you want to come? And this idiot said, I'd love to, but I have an assignment I have to finish. I probably could have got, an extension from the prof. I don't know. But anyway, I didn't go. They went down. It was clear. They saw totality. They were glowing when they came back. And I was, oh, what a stupid idiot. Now, 54 years from 1970. Oh, one more thing about 1970. Maybe the other reason I didn't want to go is Carly Simon wrote a song about You're So Vain, about somebody that flew a Learjet over Nova Scotia, and I didn't want to get into her song. Anyway, The next exoligmos is the one that we're seeing. And 2 months less a day. The greatest eclipse is still in Mexico. It's a little different. It seems wider now than it was before, and I'm surprised that much difference. But it's roughly the same shape and over roughly the same area. And lunar eclipses also repeat. So if you have a lunar eclipse, 54 years and I think it's 34 days later, you're going to have another lunar eclipse almost always. It's not 100%, but it's a pretty good prediction. Anyway, so the ancients, when they figured out the Saros and the exoligmos pattern, they could accurately predict lunar eclipses. They could predict partial solar eclipses. My guess is if somebody had an empire the size of, say, Mexico or Ontario, there's a good chance that there was a total eclipse in one place of the empire. There's going to be another total eclipse somewhere else in the empire, but not very good for eclipse chasing. Now we go into Greek astronomy. They used Babylonian records and they had mathematical models. They enhanced the mathematical models, and I'm going to talk a bit about that in a bit. Hipparchus was one of the giants of the astronomy, and unfortunately his books have all been lost. And I don't know what it is about Europeans in the Dark Ages, but they love burning most books, and it's so tragic. But it might get recovered. I just read a couple of days ago that they've got a technique where they can do, what do you call it when they x-ray something to get a 3D picture inside? Tomography or something or other. Anyway, they can do a similar process for the old scrolls that are so brittle that were burned when Vesuvius sent the mass of hot volcanic gas over Pompeii. And there are a whole bunch in libraries, and maybe one of them is the book by Hipparchus. Who knows? Anyway, that's going to be exciting because they can computer analyze these without disturbing them and read them. Amazing. Anyway, the other giant was Ptolemy, and there are allegations that he cooked some data, and there's a mission named after Hipparchus, but not after Ptolemy. Anyway, his book, Almagest, believe it or not, was also destroyed, but it had been translated into Arabic, and then it got translated back. And it was the authority for astronomy for something like 1600 years. Now, there are two assumptions in Greek astronomy, there's calculations. One, things moved around the earth, and they're not alone on that. Like the Mayans believed everything revolves around the earth, and their whole model, especially over Venus, involved that. So you have the earth in the center and the moon. This doesn't show, but they also include Mercury, Venus, Sun, Mars, and also Saturn, Jupiter and Saturn are also included it. And then the starry firmament on the outside, and all of them are moving around the earth. The second assumption was that circles are the perfect shape that God would want everything to be. So everything had to move evenly around a circle. And in particular, when you take out what we call the 24-hour cycle, there was a pattern of how the sun moved, and it had to move evenly compared to movement. But there's a problem. You can measure when the solstices are from either when it sets, when the sun sets furthest north or south, depending on which one, or you can measure it from shadows. The equinox is a little harder to measure to me. And there was a bronze equatorial ring in Alexandria, no evidence of it now. And what happens is basically you have this so that the perpendicular to the ring points to the North Celestial Pole. Then if you have a star like Altair that's north of the equator, the light from Altair will shine past one ring and might hit the other ring. If you have one south of the equator, like Sirius, it will go the other side of the ring and come up. But if you have a star like the belt of Orion, which is right on the celestial equator, a cockroach on one side of the ring couldn't see the stars of Orion because they're right over it. And in particular, when the sun crosses the equator, which is the definition of the equinox, you can't see, and apparently they could see the shadow from one side on the other, and actually they could get a pretty good estimate when the equinox was. I wish I could visit this on a equinox day, and I can't even figure it out where it is. It was from Wikipedia, but it didn't say where. And after I'd finished the talk, I found this in Beijing. And if this medal points exactly to the celestial pole, it not only is a sundial, but on the equinox day, you would have equal shadows on both sides, and they could actually find the moment of it. Anyway, the problem is the seasons have different lengths. Our summer, not Crocodile Dundee summer, but our summer is longer and our winter is shorter. And how do you get around that? And somebody thought, well, why don't we say that the immovable Earth is still, but the center of the sun's movement is a little bit offset. And then you can get equal, you can get the days to work out. And I thought for a long time that all this machinery was just pretty pictures, but it was also used to calculate. And the sun actually at 60.8 days after equinox is 1/6 of a year. And in that moment, the sun would orbit 60 degrees compared to its center of motion, okay? But if you know that the Earth's fixed location is 15% of the orbit to the left and 5% above, you can calculate that the actual seeming movement in the sun would be 57 degrees. Now, this was mostly used for planets, and they had complicated circles on circles. And this is what was used to calculate predictions for the future. Tables were prepared for astrologers. The Jupiter is moving close to Regulus, so something's going to happen, so you got to behave in a certain way. I don't know what astrologers do, but also navigators. There was all sorts of information that was useful, and Christopher Columbus used it. In his fourth voyage, he wandered all over the place and then had a problem. I heard either there were worms that were eating the boat or the mast was broken. Anyway, he limped and he ended up staying in Jamaica, landing in a beach in Jamaica. And out of the bush came some Arawak Indians. And they actually were friendly. And they gave them initially food and sent a group by canoe there. But after a while, the Indians weren't too keen to provide food. They bought food, by the way. They gave things from the boat on that. And Columbus realized there was going to be a total lunar eclipse on February 29th, 1504. So he ended up talking to them and saying, our God is really angry that you're not feeding us. Boy, our God is really powerful, and he's going to make the moon disappear. Ooh. Anyway, according to the book that his son wrote, he did this, and when the Indians saw the moon disappearing, into our Earth shadow, they were all worried, and Columbus supposedly went into a cabin, and he made rousing noises and wailing and all this sort of stuff. But what he was really doing is watching an hourglass to see about the duration. And then when he figured the predicted duration of the eclipse was over, he came back and said, my powerful God will forgive you if you keep feeding us. And supposedly he got food until they got rescued. I'm skeptical. Like, that's the sort of story that sells a book, right? And the same economics applied then. But the other issue, and I specifically bought this when I was a kid, I read some great books, including a comic book on King Solomon's Mines. And the original at the cottage got destroyed by my nephews, who are now in their 30s and 40s. But I bought another one. I didn't realize, but I found a site where I could buy comics. And supposedly the heroes, this is fiction, of course, were about to be executed by some group, and they do the same line. And interesting, the guy here kept saying, it will pass, I've seen it before, even though on average you have to have 400 years to see a second eclipse. But maybe he was in a place like southern Illinois. Anyway, I'm skeptical, but whatever. Anyway, better answers came with a remarkable period in history of the Renaissance. And it was in Europe from about 1500 to 1700. And actually, Europe was a backwater compared to China for a long time. And Copernicus was 20 when news came that Columbus had supposedly discovered blah, blah, blah. He argued that planets move around the sun. And he wrote a book, but he made sure it wasn't published until he died because he was afraid of what the church would say. Galileo, we celebrated his 1609 to 2009, 400 years for the International Year of Astronomy with all sorts of activities. And among other things, he used a telescope for the first time on many things and found that the moons orbit Jupiter. My hero Kepler did major analysis about decades of observations that were really accurate of the location of Mars. And he ditched the uniform circle idea. And there was an incredible outburst of art, like Shakespeare. These last three lived on the earth for 45 years, over 45 years together. And Copernicus lived a half century at the same time as Michelangelo, the sculptor, and the guy who painted Mona Lisa. What an incredible period of history. So I'm going to go to Kepler. And he analyzed all this data, oppositions, and he found that circles on circles on circles on circles didn't work. It worked for a while, and then eventually it gave wild predictions. And he was able to plot the location of Mars in its orbit, and he came to the conclusion that objects move in ellipses. And it's easy to make an ellipse in your computer. You make a circle, and then squeeze it, that's an ellipse. Or you can take a cone and cut it, you get an ellipse. And it has interesting properties. But a second law, I think, is more important. If a planet moves, say, 30 days, and there's a certain area that it sweeps, when it gets closer to the sun, I think I made my diagram a little bit too big, but whatever, it's going to sweep an equal area at the same time. And that allowed people, once I got the mathematics, to accurately predict where objects are going to be in the future. And this was all part of the Renaissance. Now, Newton came up with a theory that all of Kepler's laws just fall right out of Newton's laws very easily. There's no evidence that an apple fell on them, but two people made notices in their diaries that Newton had told them on separate occasions that it's there. I'm almost done. And anyway, then Euler, and the mathematics was developed to solve the many body problem, and we start getting accurate predictions of eclipses. Now, I don't think you can read it, but this was the first eclipse map according to eclipsemaps.com. And it was made by Weigel from Germany. And supposedly it was finished the day before. And just a minute, I have to move this. And the idea is it went here and across, and that was the eclipse path. And this is the greatest, the point of greatest eclipse. Sorry, I'm one too far. It's possible, if you know the exact time of the new moon, to figure out where on the earth the greatest eclipse is when it's noon at the new moon time. And they could work out where it is. It's not a north-south line if you're not on a solstice, but all that can be worked out. So the time of the new moon gives the east-west direction. But this eclipse, it is descending. And the crossing the node line is after, and from the distance and time between, you can work out how far north and south this is. So this is a very powerful way to predict eclipses once you knew the patterns. The King of Spain, and I've got the wrong King Philip here. Let's say he wanted to do eclipse chase. So he would get diplomats to find out when it's going to happen. And he would travel by boat through the Bosporus with probably a whole retinue with him and land at Crimea. And it turns out, if he had been at the exact spot predicted, he would have missed the totality. So who knows when the first successful eclipse chaser was, but the King of Spain would not have been. Halley made a prediction for this eclipse And he published this out well in advance and asked people to let him know whether it was a total eclipse or a partial eclipse where he was. And in that, he got more information of the lunar path. My guess is a bunch of royalty from Europe or lairds from Scotland or whatever would have come down and seen it because it is a stunning event. And this is actually a drawing somebody made of the corona. And now we come to our wonderful eclipse that we're going to see in 2 months less a day. And it's coming up. Strongly advise you to use eclipsewise.com. And you can actually zoom in. And where are the people from Burlington? Is that you? Yeah, you're from Burlington. And I don't know, look here, would you say your house is inside totality, like below the purple line or above it? Below? Okay, then you'll see totality. And this EclipseWise program has, yeah, I'm almost done. This EclipseWise program has, it gives the times to the second. I only copied to the minute. And when you click a spot, and I think Crocodile Dundee would agree that that's an eclipse prediction. And this is a result of 3,000 years of observations in math. And you know, there's a word for people who do a whole bunch of observations, find patterns, make mathematical predictions, and that's science. And some people say astronomy was the first science ever. So thank you very much. It's really interesting to me how it's evolved over the years. And I wonder if eclipses are a major factor in the observations that were done because the kings paid for the astrologers to do their observations to protect themselves. So that's my guess. Yeah.
Okay.
Okay.
A lot. Very interesting.
Yep.
Hi, everyone. A group of us decided, maybe a year ago that, or 6 months ago to try to get together to commit to doing something to try to get somewhere where we have the best chance possible to actually see the eclipse. I'm sure you've all heard that the climate isn't very good in southern. You can turn the backlights on. Yeah. Our climate isn't exactly great in April. We have probably a 2 out of 3 chance of not seeing it if we're here in any particular place anyway. And if you go south through the US to Texas, the chances improve all the way up to 2 out of 3, maybe, you know. And so we basically decided to target 3 places between here in Texas. And I don't want to describe the whole thing. Anyway, we're going to travel. We're going to leave a few days before. And what we're going to do is be prepared to move to the next spot if the prospects are better there than where we are, or maybe even come back north. So anyway, it started out with myself, Ron McNaughton, Fred Benedict, and another fellow who dropped out. And since then, we've grown. There's about 10 of us now. Ron?
John, can you go back to the light?
Fred Benedict, did I say? Okay, Michelle, Robin Metcalf and Jake Benbihi. And they're not here tonight. So anyway, Ron has a couple of slides and go ahead, do your thing.
This image was taken by Eddington, and it was the one for the. Sorry. He could have been. I don't know. Anyway, this is the one that proved that Einstein's general relativity was right. I'm mentioning 2 sites. Eclipsophile seems like a great weather website. And it's made by several, including Jay Anderson, who's a RASC member in Winnipeg, and also a professional meteorologist, atmosphere scientist, whatever it is. Anyway. Anyway, to me, there are basically two eclipse strategies, and one is to go to a place with a high chance of clear skies, desert areas, and the other is to be mobile, and we've decided we're going to be mobile, and where we end up, I don't know. On Tuesday, the 2nd of April, we're going to have a meeting and look at the weather information and make decisions, and it could be we'll have another meeting on the Thursday and make a final decision, like who knows where we're going to go, but we're there. And this is the path, and Eclipse Wise is a website I really recommend using. You can zoom in and get details. I was talking about it earlier. So on April 5th, we're going to leave early Friday morning and go somewhere near Indianapolis. Then this is the path of totality. Then on Saturday, we're going to end up in Blytheville, Arkansas. And then Sunday, we're still working out details, but we're going to go back into the path of totality and end up in Mount Pleasant, Texas. It's not exactly on the center line, but close. And we have bookings for the Sunday night and the Monday night. And we might see it right there, or we might drive closer to the path of totality, but we only get another, I think it's 20 extra seconds of totality. So, or we might have to drive even further south depending on the weather. So that's the plan. So John, you can.
If 1 week before, I mean, if everything looks great and somebody says it's going to be really clear, like remember that clear stretch that we had in 23 in April? It wasn't around April 8th. I think it was a week or two after that. And it was clear on April 8th too. Yeah. Yeah. So you never know what can happen. We could, you know, we might not go at all, I suppose. Although I think the chances of that are unlucky, because if anything, it'll probably be iffy, you know, right to the last minute. So, so we're assuming that we're going to keep going south, but at some point, if we're getting close to the 8th and it looks better to come back north, we'll come back north. Although I don't know if we would come back into Canada because, you know, crossing the border and whatever, it could take a while. So we would probably go somewhere like Ohio or something, and Cleveland or whatever. So, but basically, most of those 10 people that I told you are quite committed to going. I'm not actually. I'm kind of a standby member. I hope that I get to go, but I'm not sure I will. Mateo has exams around that time, so he may not be able to go possibly, but we're hoping that he can, and he's hoping, obviously. We're going to go in 2 vehicles. We're going to drive, and we have a group's IO group called Eclipse Team, which is only for those people. Also, Chris Malicki is an honorary member of our group because he has his own plans for, you know, to go with his family, and he might go east, I think he said, but he might end up, you know, depending on the weather, end up where we are too. So he's kind of watching what we're doing very closely. So, and if anybody else is interested, you know, let us know. And or just let me know, and you could talk about it, even if you want to just be a standby member in case somebody drops out, you know. So, and that's pretty much the rest. That's pretty much it for our talk.
Okay, thanks, John. Good luck to our team, and good luck to everyone else who is chasing the eclipse. And if it's cloudy, we'll just all meet in Burlington at Tim Hortons.
Bear with me, please. Anyways, my name is Matteo Stati, and today I'll be talking about the Antique Telescope Society Convention of 2023. So, to begin, what is the Antique Telescope Society? Well, it's a society that's built around antique telescopes, as the name suggests, and they're mainly known for using, promoting, and discussing about antique telescopes through 2 means. The first is the forums group, which you could access online, and is what I actually used related to the Marsh telescope I have, and I discussed about that in my previous presentation. But the other thing they do that's well known is their annual conferences. And this year they decided to go all the way to Italy to basically tour Italy and all of its antique observatories and other important astronomical artifacts. And so another question is, why did I attend? Well, first and most obvious is that it is nearly a once in a lifetime opportunity to be able to go to Italy and to not only get a proper tour of important astronomical sites with people who know all about these objects and places, but we also were given exclusive access to certain telescopes to actually use during the night that are usually never open to the public. Another important thing is that it is my first time going to Italy, and I'm actually half Italian, so it was pretty important for me. Another important reason is that I actually volunteer as a quote unquote curatorial assistant, as Randall describes me as, for the RASC Dorner Telescope Museum that will be opening soon. And all the telescopes I get to view there that are quote unquote antique made me love antique telescopes, and being able to look at very antique telescopes in Italy will help boost my knowledge and understanding of astronomy and telescopes. And on top of that, as I mentioned earlier, I have my own antique telescope, and that also boosts my interest to attend such an important convention. To continue on, we have here the schedule. As you could see, hopefully you could see, it is quite jam-packed. In fact, I only got around 6 or 7 hours of sleep every night, and plenty of hours of travel. And despite how horrible that sounds, I had a great time. So to begin, we went to this is on the outskirts of Rome, is a place called Castel Gandolfo. And the first place we went to in that town is it's called the Rome let me go back. It's called the Castel Gandolfo Gardens. And what's interesting about the gardens is that it is actually owned by the Vatican, and the Pope actually comes by once in a while to view it, because it's basically his garden. And in these gardens are these two observatories here, which house two very unique telescopes. This is the first one, and is very important for later in the trip. But as you could see, it is a very unique design. It's called a yoke mount, as I believe it's also used on Mount Palomar Observatory. But you could also see that it's actually two refractors in one telescope. One is for visual use, the smaller lens, and the larger one is actually used for photography. And the focal length of the larger one is perfectly, it's like accurately made, so that I believe when you plot out the picture, it corresponds to exactly, I believe, like a centimeter on a piece of paper. I don't remember exactly, but it was really interesting. The other telescope is also interesting in the fact that you can't actually use it for visual use. There is no place to put an eyepiece, and you can only use it for photography. Unfortunately, this one is in disarray, and the people who run the observatory are trying to get it renovated, as in fact, this telescope here was just renovated, I believe, around 3 years ago. After the two telescopes in the gardens, we then went to another observatory. It's called the it's in the, I don't remember the exact building name, but it was very close by. And as you can see here, there are two very well-made telescopes by Carl Zeiss. And if you did not know, they did indeed make telescopes this large. And unfortunately, we were unable to use them, but they are very well made. After that, at the end of day one, we went to this hotel here, just in the center of Rome, called the Prasad Palace. And unfortunately, we didn't actually sleep there, but yeah, just the Best Western for me. But what the reason why we went there is for their conference room. And for the end of day one and for basically the entirety of day two, we just did presentations, one of which was my presentation about the Marsh telescope. And we spent all that time down in that tiny room that's not air conditioned and had a great time. There was only one other thing we did on the second day, which is just a short walk away from this hotel, which is this place right here. It's one of the many churches you'll find in Rome called the Basilica of Saint Mary of the Angels and Martyrs. So this church, while it is beautiful, is uninteresting for astronomers. But one thing they have, which really piqued everyone's interest, is this right here, a meridian line that is, I believe, around 50 feet long. It goes from all the way to where I took the picture to the wall there. And it's really well made. The interesting thing is that it was actually made 200 years after the church was made. So you could see the intricate tilings being gouged out for astronomy. If you look over here, you could see the small hole in the wall all the way up near the roof, also gouged out. And the light travels through that hole. And there was once a lens in there to further magnify that light. And it goes all the way back to the line or near the line. And as you can see in these pictures here, as noon approaches, the light directly hits the meridian line at noon. And as you can see here, on the day we went, it was day 113, according to the calendar that comes from that meridian line. Moving on to day 3, we were also near Rome, this time in a place called Monte Mario, on top of a large mountain, like most observatories should be. And as you can see here, we went to a place called the Copernicus Museum. And it's a very nice museum dedicated to Copernicus. Unfortunately, the observatory on top was not in use. You could also see one of the many birds that were flying about. Got lucky with a mid-flight picture there. And inside we could see many some of them made out of wood, but also paper made telescopes. But not just any paper. It's like a very hardened paper. I forgot what it's called, but it's really intricate and well made. And on top of that, a highlight of the museum is this beautiful portrait of Galileo that is about 10 by 10 feet across and is really intricate and detailed. After there, we went to a place called the Monte Porzo INAF Observatory. And as you can see here, one of the key stones of the museum part of the observatory is this large transit telescope. And after that, we have a few more interesting things. They have a lot of astronomical objects, and I just wanted to show a few of them. On the left is a interesting telescope that actually is 4 in 1, as you could see with the 4 different focusers. And I believe each one had a different filter where you could see a small diagram of the sun in different filters as an example. The one on the right is actually a very ornate telescope made for a very rich person who did not care about astronomy and never used it. And the middle is actually a very intricate measuring device that was placed near telescopes and observatories to measure all sorts of things, such as earth tremors, wind speeds, temperature, all sorts of things. And fortunately, I didn't get the best picture of it, but it was really cool to look at. But as you can see here, I don't have a picture of the main telescope, and that's because there isn't one. The story goes is that this observatory was being built near the end of the Second World War. And so Italy, I believe directly from Mussolini's orders, he basically he bought a telescope from Carl Zeiss, and Carl Zeiss was Zeiss was making the telescope in Germany, but the Allied forces took over at the end of the Second World War in that part of the world, and the telescope never arrived. So we had a whole observatory in Italy with no telescope. So the owners of the observatory turned into a part library and part museum, as you can see with the many books around the pictures. Moving on, we have an intermission before we get to day 4 of some of the many foods I ate, all of which were great. So, moving on to day 4, we move all the way from Rome to Florence. And the first thing we went to is a place called the Museo Galileo, which was, in my opinion, the best part of the trip. As you could see on the left, we actually have another meridian line, but it's actually the opposite design as the one in the church, where the shadow of that monolith casts the marker that goes to the meridian line. On the right, we have this very ornate astronomical clock with 11 different dials. Unfortunately, it's all not in English, so I had no idea what each dial was. And the center one, which I believe a lot of people have already realized what that is, but that is actually Galileo's middle finger. The story goes is that there was basically a cult-like following to Galileo, and after his death, some of the people who followed him a lot decided best it was to rob his grave and take some of his belongings, like that. And it ended up there. A few more interesting things from this museum was this on the left here, this very ornate celestial sphere, I believe it's called, where this Earth is in the center, and all the different rings around it were of the different planets, the moon, the sun, and at the very end was the stars and constellations. And all those little notches aren't gears, but they're actually measurement markings. So it was so people could somewhat accurately determine where things are in the night sky. And on the right is a very large telescope called the Amici telescope. And I believe it was built in the early 1700s and was actually the largest telescope in the world when it was built. And finally, the most important part of this museum, Galileo's telescopes, the real ones, in all of its glory. I don't really have anything to add to that. So after that, we headed to an observatory called the RASC Observatory. It's I believe it was still in Florence, but it was out in the mountainous area. On the top is just a cool little display telescope they had in their library, and the bottom is a panoramic view of just how beautiful it is there. And an interesting fact about this place is that just a few kilometers away was Galileo's house, which unfortunately we were originally going to get a tour of the house, but it was canceled without any reason. But anyways, the main feature of the observatory is the telescope itself, which is this 14-inch refractor. It's I believe around 30 feet long, something like that. And it was it's beautiful to look at. We were going to do solar observing with it, but something went wrong with the mount, so we just got a tour of it instead. But it was still beautiful to look at nonetheless. Moving on to day 5, we moved from Florence to Milan, and the first place we went to is the Milan Brera Astronomical Museum, which featured many different telescopes and astronomical objects, such as these very large telescopes. On the left is I believe, around 12-foot tall astronomical clock for sidereal time. Very nice transit telescope. And on the right is actually a model of the telescope they have, of a big telescope they have there. I don't think there's a name for it exactly, but here it is for real. And as you can see, it's made out of wood. I believe it's a 10-inch diameter or 8, but it was very nice to see. But the most interesting feature is the mount, where if I could play this here. So it actually has this pendulum-like design, which I'm not sure exactly how it works, but it helps with tracking the night sky. Moving on, we go to a place called the Leonardo da Vinci Museum of Science and Technology. Now, this museum isn't dedicated to astronomy, so it's actually really large and had many different subjects, such as Earth, like air travel with like planes and ships. And as you can see on the outside of the building, we have a model of a European seat of a ESA rocket. And on the inside, the most important thing we saw is this, an even larger telescope than the RASC telescope, somehow put into a museum, a 20-inch refractor called, and I believe it's made by MERZ, MERZ. And on top of that were these two large, one's a globe and the other's a celestial sphere, 1 meter in diameter and of incredible value. And on top of that, they had a space exhibit that was collaborated with the ESA, such as a model of one of their satellite ships, one of the very first ESA suits, as well as some of the watches that went into space. And finally, the last part of our journey is this place here called the Rosano Civic Astronomical Observatory. Now, there's nothing too special about it, but the fact that it was made by just locals doing just a simple local astronomical group is amazing, because just them alone funded this observatory and this 6.25-inch telescope that was imported from London. And it was a sight to behold, as the dome type, this clamshell dome, is actually the largest clamshell observatory in the world, I believe. And we were actually able to use this telescope, which was very nice, and I very much enjoyed my time with it. And that is all I have for tonight. Thank you very much. I'm not sure what it's called. It's from the 1800s. It's brass. I don't remember who made it. Yeah. Yes, this is Milan as well.
What?
Oh, so yeah, they are benches. It's a unique story. I believe what they do is they actually have like it's almost like an outdoor, like a movie theater or something like that. It's very unique. And on the other side is like a wall of a school, which is where this is built actually. And I believe they use a projector to like show like presentations and movies and things. I'm not exactly sure the design behind that, but it's very interesting. Any other questions? Yeah. So it was mainly trains to get from city to city, but we actually got a bus, like a large, almost like a Greyhound bus, to get us from observatory to observatory for shorter travels.
How many people were on?
I believe it was around, was it like 20 something in total? But not everyone attended every event, as the schedule was, it's not easy to follow through with every different section. Oh, well, I guess I should give backstory. So when my research with my Marsh telescope led to the ATS forums, I talked with them with like my telescope, and then I did research on the Antique Telescope Society, and that's when I learned that they do the yearly events, and they actually normally only do it in the United States, which is where most of them are based off of. but this year was different. And after seeing my interesting discussion about the Marsh telescope, I talked to the person who runs the Antique Telescope Society. His name is Bart Freed, and he was huge help. He was a huge help during my investigation of the Marsh telescope, and he talked to me a bit over the phone, and I also mentioned that I made a presentation about it, and he said, "Oh, maybe you could present for the next Antique Telescope Society convention." Oh, yeah, and that's how I ended up there. Yeah. Yeah, well, we actually got a one of the employees. He was very knowledgeable about all the items in the museum. Yeah, he said it was made in the, I think, like mid 1500s. It even came with like a whole manual on how to use it. Yeah, it was quite interesting. I don't remember the whole story behind it. Oh, you mean of Copernicus? I don't remember who painted it. Yeah, unfortunately, this was all done in October, so I don't remember all the details. I don't think that's him on his deathbed. I don't remember, but they kind of made him look like quite the important person. Well, he is, but I mean, just look at him.
When we were there, they told us that Galileo's middle finger was actually oriented to point towards the Vatican. I'm not sure if that was true. I'm not sure if that was true, but okay. Thanks very much to our speakers tonight.